Phyllotaxis is the unique spiral-like arrangements you see in plant forms. And on the left here we have an aloe demonstrating beautiful phyllotaxis, and on the right we have the sunflower, which is used as an example quite often. And this spiral-like pattern comes from the golden angle, which is a angular ratio that's based on the golden ratio. And I can best show you that with a little drawing here. On the right hand side we've got a line, and we've essentially divided it into two parts, A, which is bigger, and B, which is a bit smaller. And this division right here is a really special point along this line. This is the point at which A over B is equal to A plus B, whoops, I can draw that a bit better, A plus B over A. So what's that? That's essentially saying that the ratio of the length of A to the length of B is actually equivalent to the length of the whole thing, right, which is all of this right here. So this is the whole thing right here over A. And there's only one point at which that happens, right there. And if you're interested in the math behind how to derive that precise value, there's a great Khan Academy video I will give you guys a link to. Nevertheless, the algebraic equation for deriving phi ends up being, and this comes from actually solving a quadratic, 1 plus the square root of 5 over 2, which, and I should say approximately, gives us the value of phi. And don't confuse this with the phi we were using earlier to describe angles. So it gets used here in a different way. And in terms of the golden ratio, phi is equal to approximately, if we were to calculate this out, 1.618033. And it goes on and on and on. So this special number encodes this beautiful relationship between A and B and their overall, the sum of their lengths over A. And the golden angle emerges from this relationship when we consider a circle with, let's say the entire circle, this entire angle going all the way around 360 degrees, right, or 2 pi radians. Let's set that equal to 1. And if we wanted to know, and I should draw this maybe in orange, if we wanted to know what the golden angle was, it would be, let me bring out the ruler here, draw this nicely. That looks roughly right. Then really what the golden angle is this guy right here. This is A, the larger percentage of the larger, the Pac-Man, and the smaller angle is B. And again, the same relationship holds. The angle A over B is equal to A plus B over A. So it encodes that same relationship, except now it's angular. So, and this right here is roughly equivalent to 0.382 if we were to work it out. And in degrees, that's like 137.5 degrees. And to get the value of this in radians, we could also simply just multiply this, since this is, we're now dealing with, this is, because this is 1 unit, and that's 1 unit is equivalent to 2 pi radians, we would just multiply this by 2 pi to get it in radians. Equals the golden angle in radians. And much like before, what we're going to do is we're going to start with a point here and I should choose a different color. Let's choose black. We'll start with a point in the middle, and we'll have a control for the number of points we want to generate for a golden spiral. And with each point, we're going to track an angle, and we'll call it theta, so it doesn't, confuse us with phi here, which is now referring to the golden ratio or golden angle in our case. This will be golden angle. So we'll call this angle theta, and it will start here. It'll be at 0. And we will, as we iterate over our set of points, we'll say we have 100 points again, some uniform even number. As we iterate over the number of points, theta, which starts at 0, is going to be increasing by by this value, the golden angle in radians. So each time through, we're going to add to theta the golden angle. And I should write that as plus golden angle, right? And as that value is increasing, we're also going to increase our radius as well, because we're going to be generating these in polar coordinates. And so we're going to draw the next point here with an increase in radius, and then another point here, and we'll just keep iterating and increasing this angle theta and increasing our radius to produce the golden spiral. That's all there is to it. And it's going to result in an incredibly uniform, and the sunflower I think shows this pretty well, a very uniform packing of circles. So it's great for the sunflower because it can fit seeds in there very well. These are actually sort of diamond shape. The wedge shape works even better. But nevertheless, if you have circles, this is a great way to pack them into a larger circle with minimal gaps between them. So they would pack very, very tightly. This drawing is not very accurate, but you get the idea. So let's go ahead and start implementing that in Houdini.